All right, um, so we're talking about maximum and minimum, and these can be difficult. Oh, pencil. Do you ever get a pencil, Kelsey? Oh. I am. Thank you. I got her going already. I know. I'm on top of it today. It's a good Monday. It's been a good Monday so far. So we'll see. We'll see how things go. It's always a good Monday. It's always a good day when we get to do the Shanghai problem. It's always one of my favorite days too. So, all right, and I'm sure it was yours this weekend. Now, so as we saw, hopefully you saw here a little bit that these optimization problems, max-min problems, can really run the gamut from difficult to easy, depending on, or easier, depending on how easy the first three steps are. Because these steps here are simply the ones we learned in chapter 2. How do you find a global max-min of a function? Well, you check where the derivative is 0, you check where the derivative is undefined, you check the endpoints, and by check, we mean you identify those, but normally you're given the endpoints, the derivative, set it equal to 0, see where the derivative is undefined, then you use a list of candidates or a number line or some way of showing that it's a max or a min, and then when it's a story problem, you actually answer the question. So the questions we had when we got to chapter 2 were simply this. Here's a function. Between these two endpoints, find where it has its highest and lowest point. Well, you did the derivative, set equal to 0, found that, check to see if it's ever undefined, look at the endpoints, you take those values, your critical points, your endpoints, you plug those into the function, you see what's the highest, what's the lowest, that's your max and your min. Okay, then we talked about what happens if there are no endpoints. If there are no endpoints, and you do the derivative, set it equal to 0, and check where the derivative is undefined, and only have one candidate, we said, well, then if you only have one candidate, you can't really do a list of candidates to compare, so you have to do some other things. One thing's a number line. So you could say, well, at this one place where the derivative is 0, we check the derivative on both sides with a number line. It's positive then negative, so that tells me f changes from increasing to decreasing. Now you'd want to use the word always. You'd say, well, the function is always increasing before this and always decreasing after this, so therefore this is a max. Or you could, if there are no endpoints, you could kind of say, well, the endpoints would be, the end behavior would be when x goes to infinity or when x goes to negative infinity and see what's happening. And in this function, it would be going to negative infinity, both of those. So you could know that it's a max that way. So that's the stuff we already learned in chapter 2. Now, we didn't talk as much about these one candidate situations. We didn't get into that quite as much. And we do get into that quite a bit in some of these problems. So that's this below the blue line part. So we need to be pretty solid on that. Now, where people usually screw up is they don't do enough justifying that it's a max or min, or they forget to check where the derivative is undefined, or something like that. So make sure you go through those steps. The difficulty comes in these top 3 steps. Now, the easy problems in the homework, of the 5, and I would say 4 of them were pretty easy. Well, 3 should have been pretty easy. The first one, number 4, was a little more challenging, and then 17 was really challenging. And they became challenging because of this part. Identify what you're trying to maximize or minimize. Write an equation for that quantity, and step 3 is really the tricky one sometimes. Get that equation in terms of a single variable. And that's what was so hard about 17. Okay? So let's take a look at these problems and see if we can kind of figure out what's going on. So here's number 4. Now, on number 4, you got to start with a picture. Now, what are we trying to minimize in number 4? The length of that line, the distance of that little segment, right? Now, some of you, I helped several people this morning at lunch and answered a few questions. And some of you went back to example 3, which the direction said to, and you just used that same distance equation they had. You can't do that because it's a different distance. In the example, they were going from this point down to the origin. In this problem, you're going from this point to the point 0, 1. So what does step 1 say to do in our little recipe? Find what you're trying to minimize or maximize. Well, we're minimizing distance. So what we need is a distance equation. Well, the distance formula is this. Right? Subtract the y's, y1, y2, whatever. That's what we're doing. Okay? So you need to do x minus 0 squared, and you need to do y minus 1 squared for your equation. So it should look like this. See, and the minus 1 part is the part some of you were leaving off because you didn't realize that it was a little bit different problem. So you had, okay, so that's your distance right there. Now, by the way, I don't know if anybody thought of this, but this is a problem you could have done in 9th grade geometry. You don't need calculus for this problem. What's the shortest distance from a point to a line? Well, but they could intersect a lot of places. Perpendicular, right? The shortest distance from a point to a line is perpendicular. Well, what do you know about two lines that are perpendicular? Opposite reciprocal slopes. So this line right here has a slope of -2. So this little line has a slope of 1/2. So therefore, this little piece right here, this little red piece, would be the line y equals 1/2 x plus 1, because it's got a y-intercept of 1, and it's got a slope of 1/2. And so this little red line would be this, and the blue line is this. So where do those two intersect? Would simply be solving this equation right here, right? Add 2x over to here, that'd be 5/2 x. Subtract 1 over there equals 1. Divide by 5/2, you get x equals 2/5. So this problem does not need calculus. Now, if I put this on the quiz, that would not be an acceptable way to solve it, right? We're in calculus class, so we wouldn't do the calculus way to do it. But this would be, this turns out to be one that wouldn't need that, because we know the minimum distance from a point to a line is the perpendicular distance. All right, so back to what I had here. So here's my distance equation. Identify the thing you're trying to maximize or minimize. Step 2 is write an equation for that. Well, distance is the distance formula here. So we would have this. Now, what do we know that y is, by the way? What's y in this problem? It's right here. Y is -2x plus 2. As a matter of fact, that's not a bad habit to get into here. When you label an unknown point on a curve in a problem, you can label it x, y if you want, but you might as well label it, because a lot of times you know the equation for the curve. So instead of labeling it x, y, so you have two variables, label it like this, x and then -2x plus 2, and then you have just one variable. Okay, so you can set it up this way and then substitute, or just think of it that way. But anyway, there's your distance equation. Now, you get to use your calculator for these derivatives and stuff and the solving. So I don't care if you simplify this, but on the midterm, I'm talking about our quiz, which, by the way, is probably going to be Monday. I don't think we're going to quite be ready by Friday. I don't like to do a Monday quiz if we can avoid it, but that's the way it's going to work this time. Okay? So on Monday's quiz, you'll get to use your calculator to do the derivative, to solve, whatever. But you're going to have to write them on your paper, but you wouldn't have to work this all out by hand. But if I did, because on the midterm you might get one like this where you have to do it by hand. So this is going to end up being 5x squared plus 4x, I think, plus 1, I think, in here. Or no, is it minus? I think it's minus 4x, actually. Yeah, it's minus 4. Okay? Now that would be to the 1/2 power. Okay, so now when I do my derivative, I'd have 1/2 5x squared minus 4x plus 1 to the -1/2. Then times the derivative inside, which would be 10x minus 4. Okay, and I'm going to set that equal to 0. Well, this negative power would flip to the bottom, so I'd end up getting 10x minus 4 over 2 times the square root of 5x squared minus 4x plus 1. Got to be able to do these derivatives, all right? Now, in Monday's quiz, we'll get to use our calculators and so forth. Now I can divide that 2 into that, and that'd be fine. But, all right, now, get your calculators handy here. So we do our derivative. So on this one, so this was a medium. I mean, this was a little harder because we had to realize we had to use a distance formula. But once you kind of got that set up, it isn't horrible. But it's not nearly as easy as 9 and 11 and 22. I mean, 9, 11, 22, it pretty much gave you the formula. I mean, so those should not have been that tricky. Okay, other than it was our first day doing them, so it's not going to be that easy. But those would definitely be ones that you need to be able to do for the quiz. 17 is probably a little harder than what you're going to have in this first quiz. Okay, and you'll see what's difficult about it and why you wouldn't have known what to think of here. But the rest of them, for sure, we should be able to do. All right, so we got distance formula. We get it set up. We do the derivative. All right, now let's talk about this from a no calculator perspective just real quick. If you get a fraction like this and want to know where it equals 0, where does a fraction equal 0? When the top is 0. So 10x minus 4 equals 0. We solve that, we get 2/5. Oh, look at that. 2/5, right? Same thing over here. But for us right now, that's just one candidate. That's just one candidate. Now we got to talk about d prime undefined. Where's a fraction undefined? The bottom is 0. So often when you do a problem with a function, you do the derivative and it comes out a fraction, you're going to look at both parts, the top and the bottom, because the top is where the derivative would be 0, and when the bottom is 0 is when the derivative would be undefined. Now, when's the bottom going to be 0? Well, not 2. It's just really all we got to do is check this inside thing, right? So solve this on your calculator. Solve 5x squared minus 4x plus 1 equals 0. Because you can't type in your calculator and ask where something's undefined, right? I mean, there's no solve for that. So where's the derivative undefined would typically, for us, for what we're doing right now, it's when the bottom is 0. If there's no bottom, you're probably okay. So when's it 0? Well, when that thing inside there is 0. So solve that. What do you get? False. So that tells you it's never 0. So d prime undefined, never. Now make sure you're writing this down though, right? Make sure that's on your paper. Where people tend to lose points on these problems, even when they do everything right or get the right answer, is their justification and their work and following these steps, because we want to make sure we do this. Okay, so it's never undefined. We got one candidate here, and there really are no endpoints in this problem. Now, why not? I mean, what would the endpoints be? What would you think about in this problem for endpoints? Why? Because remember, we're talking about the inputs, right? When we're talking about endpoints, we're talking about what's x. Usually our input is x. What's the littlest x could be? Well, what that means is, where could this point be? This point could be way over here, and this line goes forever, right? So it could go way out to here. Our x values could go way out to here. Of course, the distance is getting farther and farther away, so clearly that's not a minimum. So you could discuss that. You could actually write a little paragraph discussing that. Or you could do your list of candidates and talk about x going to infinity and x going to negative infinity, and talk about x equals 2/5, right? And put 2/5 into your distance equation, right? So you put 2/5 into your distance equation here, get that distance, and then talk about what happens in infinity and negative infinity, and what's going to happen is it's going to get bigger and bigger and bigger, the distance, and so that's not going to be a minimum. Or you could do a number line, actually. Anytime you don't have endpoints and you have a one candidate situation, probably the easiest thing is to do a number line. D prime, put a number here, you get negative, you get a positive. Okay, when you plug that back into your d prime here. And then you'd have to say something with the word always, like we were saying a minute ago. D prime's always negative before 2/5, always positive after 2/5, so therefore d is always decreasing and always increasing, so you have a minimum at 2/5. And then you have to answer the question. The question, I think, wanted the coordinates of this point, right? So x would be 2/5. You'd have to plug that back up into this equation up here to get y. I think it comes out like 6/5. So the point would be 2/5, 6/5, I think, is the question that they actually asked. what point on that line is closest to 0, 1. Okay? So you got to make sure you have all the pieces in here. All right. Now, we'll go a little faster on some of these. Now, so here's none. And this is why this one's so easy, because well, first of all, they based it off one of the examples. Don't worry about what they said in the problem, where they said, do this one without implicit differentiation. Because in the example, they do it with implicit differentiation. Rarely will I do a problem like this with implicit differentiation. Why would you do implicit differentiation? Well, because sometimes you get more than one variable, and it's tough to get it down to one variable. So you could do implicit differentiation. The problem is, you're still going to have some extra information before that works. So if you've already got the extra information, just substitute and get it down to one variable. That's the easiest thing to do. So I wouldn't worry about how they did it with implicit differentiation. But so they tell you you're doing the product, so you got this equation. They tell you the two numbers have to add up to 10. This is just like the one we did yesterday as an example. So you solve this for y. You get 10 minus x. You substitute that right into there. So you get this. There's step 3. Right? Product is what you're trying to maximize. You got an equation for product. So now how do you find the maximum? You check where the derivative is 0. You check see if the derivative is undefined. And you think about your inputs. Here, the smallest x could be a 0. The biggest it could be is 10. We get one candidate, which is 5. Now, again, you have an option here. You could make the argument that 0 and 10 are not endpoints. Why? What did it say in this problem? Well, it talked about a reasonable interval, but what did it tell you about what the two numbers had to be? They add to 10, but what else did it tell you about the numbers? Oh, it just said non-zero? Or did it say positive? Or did it say... It didn't say at all? Oh, they just said non-negative. Okay, two non-negative numbers. So it could be 0, right? Okay, so in that case, then it does make sense to say 0. So the littlest x would be 0. So they're non-negative. And the biggest x would be if it was 10, because, right, if it's bigger than 10, then y would have to be negative, and it can't be, right? So the biggest it could be is 10, and that'd be 0. So 0, 10. So that could work, right? So you could do true endpoints here. But if it would have said two positive numbers, then you could make the argument, well, x can't be a 0. So you really, and you can't let it be 1, because what about 0.5 or 0.1 or something, right? So there you'd make the argument, well, there really aren't endpoints. So then you could do it with a number line. And this happens in the real world type problems what we get into is sometimes the endpoints really don't make sense in the problem. So if you would prefer to leave them out, then a lot of times it turns into a one candidate problem, which you could then do a number line on. Okay? So either way would be acceptable to me here. All right, so that's a max, and then answer the question. 11 is very much the same thing. Now, one difficulty I saw people having is they don't know what to call this one in 11 because they didn't give it a name. They just said, find the minimum, was it minimum? Find the minimum value of this expression. So I just called it E for expression. Yeah, call it something. Like if we're finding the max volume, it's V equals. If we're finding the max profit, we put P equals. Or the max product on that last problem, we put P equals. So here we're doing so call it something. You got to name it. All right. And then they said x plus y equals 4. So again, solve for y over here. So you start to see some of the similarities in these problems. We substitute that in for the y, you get this. So now we want to do, so now we're at step 3. We got the function that we're trying to maximize or minimize. So we do the derivative. We set it equal to 0, we solve, we could throw out the negative one here because they did say x is greater than or equal to 0 in the problem. So now that's interesting, x greater than or equal to 0, that gives me a left endpoint but doesn't really give me a right endpoint, which is okay. So I need to talk about infinity maybe as my right endpoint. So I need to maybe discuss that. So I get 3 over 3, we look at E prime, it's a simple parabola so it's never undefined, so we write that down here. So I do my candidates, I put in 0, put a root 3 over 3, and then I say, what happens if x goes to infinity? Well, you can see it's x cubed, so it's going to just get bigger and bigger. So that truly is my minimum right there. Okay, so to me, 9 and 11 are pretty easy. I mean, so when it comes down to what we have to do for the quiz on a max-min problem, if you get one of these where they've basically given you the function you're trying to maximize and minimize, and it's just about knowing the steps that you have to go through. So I'll probably give you a mixture of those kind of things. All right, we'll skip 17 for a minute. We'll come back to it. Let's go to 22. So 22 is kind of the same thing as 9, really, just in more of a real-life setting. They say you've got a fence, or you want to fence in a rectangular region, and so they want to know what's the max area you can do for $40. That's $1 per foot for fencing. And then they tell you even the perimeter formula. So I went ahead and drew this. Now it turns out you may have learned this in geometry too. I remember talking about this when I was in geometry, or when I taught geometry, but for a given perimeter, the max area is always what shape? A square. And it works the other way too. For a given fixed area, the shape that will give you the minimum perimeter is a square. Okay, so if I was going to build a cow pasture and I wanted to hold the most possible space for the least amount of fencing, I would build it as a square. Now, when that changes is maybe you want, well, maybe you've got this fencing and up next to a barn. So on this side, you don't need any fencing. So you only need fencing on 3 sides. Well, then it wouldn't be a square. Okay? The max area for the least amount of material would not be a square. Okay? Or if maybe the cost of fencing on these 2 sides was different than the cost of the fencing on these 2 sides, for whatever reason, then it might not be a square. Okay? But just for a basic situation like this, it ends up being a square. But we can go through it here. So if it costs $1 per foot, and they said you want to spend $40, so your perimeter's got to be 40. So here's your equation. So we go ahead and solve it for y, and we get this. So we substitute that in because we identify what we're trying to do. We're trying to find the max area. So we get our area equation. We substitute that in. Here's our area equation right here. So step 3 was pretty easy to get to. Okay? So we do the derivative, which is this. We set it equal to 0. Whoops, forgot that. Set it equal to 0. Get our candidate. A prime is never undefined. I forgot that too. Geez, I didn't do that good. A prime is never undefined. It's a 10. Now again, here's where you could say endpoints don't really make sense in this problem. What's the smallest x could be? 0. Well, then you don't even have a square. If x is 0, you don't even have a rectangle anymore. What's the biggest x could be? Well, you could say 20. You could use all $40 for the length. So you could have 20 here and 20 here. But then y would be 0, and again, you wouldn't have a rectangle. So I don't care. I will let you do that if you want to. If you want to use 0 and 20 as endpoints and do a thing here in a list of candidates, that's fine. But you could also do this as a number line. You could say the endpoints don't really make sense, so my only candidate is 10. Do an A prime kind of number line, and then explain it. Again, if you do that, make sure you write it out and say always, that stuff. A prime is always positive before 10, always negative after 10. So A is always increasing, then always decreasing, so it's a max. Somehow you got to justify that that is a max. Either your list of candidates, number line, something to that effect. All right, let's talk about 17. Now, here is the situation. All right. Now, I told Ryan yesterday to text out everybody a picture of this situation, so if you didn't get one, sorry, you've got to blame me. Who'd you send it to?
Kelsey.
Kelsey. Okay. And that was only after I told you like 3 times. All right. after she had texted me and asked me. All right. But anyway, uh, I thought about putting it up on the website, but even then it's not that helpful. But what I've done here is I made up a quick little interactive thing just to see the situation. So University of Shanghai, which Allie and I were talking, evidently none of you are going to go to the University of Shanghai. But that's okay. But like I said, you haven't graduated from high school yet, right? I mean, so we'll get there. By the end of the year, we'll be able to do this, and you'll be fine if you want to go to Shanghai. But what we have, it says that there's the parabola fits snugly inside of a triangle. Okay, so the key word there being snugly. Yeah, that's the technical mathematical term for this. To fit snugly in there means that the edge of the triangle, it means we have a tangent. We have a tangent line to this curve. Okay? And what they're saying is to find where this triangle touches the curve that will make the triangle be a minimum. Because if you look at this, as you move this point up here towards x equals 0, the triangle gets really big. The area gets really big. Matter of fact, up here it would be infinite because the line would be horizontal. But as you move it down here, the triangle area, it's kind of measuring right here, the area is getting smaller. But then you get past about here, and now the area starts getting bigger again. So the idea is that somewhere in here, the area is a minimum. And then now we need to find that point. Okay, so this helps you to at least see what the situation is. Okay, so this is the picture that I've drawn. And I think this would be a good picture for you to draw as well. And label it. Now, even with that, I don't know that this was going to help you a whole lot because you weren't going to need, you weren't, I don't think, going to be able to figure out what to do with this information because you haven't ever seen this before. But from here on out, we will refer to this, what we're about to do here, we'll refer to this as the Shanghai problem. Or 2 days from now, we're going to do a similar problem that involves Luke Skywalker. So I sometimes refer to it as the Luke Skywalker problem. So my hope is a month from now, 2 months from now, when we run into a problem that's got this idea in it, that you'll read it and you'll go, hey, this is a Shanghai problem. Or this is a Luke Skywalker problem, I hope. Okay? And it'll trigger this idea of what we have to do for this. Okay, let me explain what's going on here. We have a tangent line to a curve. We've done that before. The difference is, before, say I ask you to write the equation of tangent line. Well, what we always had in the past was we knew what the curve was, and we knew where the point was tangent to the curve. So we'd say, find the equation of tangent line at x equals 2. So you do the derivative, and you plug in a 2. And that'd give you the slope. The Shanghai situation, the Luke Skywalker situation, is a situation where we have a line tangent to a curve, but we don't know where it touches the curve. We're trying to figure out where it touches the curve. But to do that, we're going to have an extra piece of information. If we don't know where it touches the curve, then we got to have something else. Well, what we have is we know some other points where the line touches something. Not the curve, but something else. And that's what we know here. We know a couple other points on this line. We know the x-intercept, we know the y-intercept. Now, we don't know what they are numerically, but we can at least label them. Okay? That's the Shanghai situation, is when we have a tangent line to a curve, but we don't know where it touches the curve. So we got to have some other information. Okay, so now let's back up a little bit. And let's get to our max-min question. So, step 1, identify what we're trying to maximize or minimize. The area of this snugly triangle. So we need the formula for the area of that triangle. Now, mine's actually wrong here.
That's why.
It is?
Yeah.
Oh, really? Oh, could be. The way I've labeled this, I labeled this as B, comma 0. but that's only measured from the y-axis, right? So it's b to there. So my red triangle actually has a base of 2b, right? So the base is 2b times the height, and then divide by 2. So the 2's would cancel. So the area of my red triangle, the way I've labeled it, is actually just b times h. Okay? B times h. I've done this before where I labeled this point 1/2 b. Right? But then it just gets messier because it's got fractions and stuff. Okay? So I'd rather just do it this way. All right, so step 1, identify what you're trying to minimize. We want to minimize the area. Step 2, write an equation for that. We got it. Step 3, get it in terms of one variable. This is where the Shanghai problem is really hard, especially the first time you run into this. How in the world can we get this into one variable? Well, we're going to use these points over here and what we were just talking about. All right, so what do we know? Well, we know we have a line and we know it's touching this curve. Well, by definition, that's the derivative. The slope of it is the derivative. So, one thing I can do is do the derivative of this point, which I've done right here, negative 2x. So that tells me the slope of this line right here, negative 2x. But I also know that the slope of this red line right here could be found by taking these 2 points and doing a slope calculation, right? Just a y2 minus y1. So that's what I've done right here. Y take away 0, and x take away b. So this and this are equal to each other. Those two things are the same. They're both the slope of that line. One's the derivative, one's the slope between 2 points. Now, let's stop right there and just let's lock that in here a little bit. Maybe make a note to yourself in your notes. That is the Shanghai solution right there. That's the key to Shanghai. The key to Luke Skywalker. So in the future, when we say, hey, that's a Shanghai problem, what we mean is find 2 ways to write the slope of that tangent line. One way is derivative. The other way is slope between 2 points. Because what we're gonna have to know 2 points. We're gonna have the one where it touches. Now when I say no, we're not gonna know what they are, but we're gonna need to have 2 points and some information about 2 points. So here I've got the place where it's tangent. We're calling it xy. And then we've got a place out here somewhere. And we're calling that b comma 0. And so I can do the slope between those 2 points, and I can do the derivative of the curve. And that gives me 2 ways of writing slope, and I can put those 2 equal to each other. So I can now do this. I can now do negative 2x equals y minus 0 over x minus b. Now, I should have done something that I mentioned a while back. I shouldn't have y in there. What should I have? Yeah, I should have made this point x and 1 minus x squared is what I should have done. Because we know that y is equal to 1 minus x squared. So let me do that now. So I'd had negative 2x equals 1 minus x squared minus 0 over x minus b. Okay? Okay, now, it's easy to get lost in the weeds here because we all have stuff going on. What am I trying to do right now? I'm trying to get this in terms of one variable, right? So you say, well, big deal, what's this do? Well, this is going to let me solve for b. And I can plug that in there and you say, well, so you're still going to have x. Well, right. But then we could do the same thing with this point and this point, right? We could take these 2 points and do a slope. That's what I did down here. I can take these 2 points and do a slope, and that's also got to equal negative 2x. And then I can solve for h. Okay, that's what we're going to do. All right, so back to this. Now, at this point, you could use your calculator. You could do a solve on your calculator and tell it to solve for b. Now, I think we can do it just about as fast without the calculator, because it ends up working out pretty nice. So I'm going to multiply the x minus b over here, so I got to distribute. And then I'm going to add the 2x squared over there. So that'd be 1 plus x squared. And then I'm going to divide by 2x. I have 1 plus x squared over 2x. That wasn't too bad. So now in place of b, I have 1 plus x squared over 2x. Okay? Now I'm going to do the same thing with these two yellow points. I'm going to do y minus h, which would be 1 minus x squared minus h, over x minus 0, which is just x. And that's got to equal negative 2x. Because again, those both are the slope of that line. Slope between the two yellow points and the derivative are both slope of that line. So now I multiply the x over there, I get 1 minus x squared minus h equals negative 2x squared. If I move my h over to the right, add the 2x squared over there, I get 1 plus x squared. So h is 1 plus x squared. So now I am done with step 3. Now it might be nice to rewrite that a little bit. That would be 1 plus x squared all squared on top of 2x. Okay. Well, you can't bring the 2 up. You can bring the x up. I think it's easier to do that. But to be honest, again, you get to use your calculator. So at this point, I'd probably go to my calculator and do the derivative. Right? It wasn't too bad to simplify, but at this point, you'd have to do a quotient rule, which I think is probably the easier way to do it, to be honest with you. You could do a quotient rule for the derivative. Maybe by the time you type it into your calculator, you could do it better. I don't know. Derivative at the top, it's going to get a little messy. 1 plus x squared to the first times the derivative inside is 2x times the bottom left alone minus, it's going to get messy. Be fine, but you could do it, okay? I'm going to let you finish that from there, and you should. You should go through that process. But, again, we've done the hard work. We're now at line 3. We've got the thing we're trying to maximize, in this case minimize, in terms of one variable. But we just never have been through that Shanghai situation, so we would never, it would have been really hard for you to think of how to do that. Okay, I knew that going into it, but I wanted you to do some thinking about it. All right, but now that we have that equation, do the derivative, see where it's 0, see where the derivative is undefined, see if there's endpoints, list of candidates, all that stuff. Finish with all that stuff, okay? But that's it. So now on Wednesday, when we do this Luke Skywalker problem, there's going to come a point in there where I'm going to say, it's like Shanghai. There's a tangent line. There's going to be 2 different points on it. You can do 2 different slopes, set them equal to each other. You do the derivative, you do slope between 2 points, set them equal to each other, and use that to help you in the problem. Okay? All right. Invariably on the AP test, which means maybe on the midterm, maybe on the final, there's one of the free response type problems has a component to it with tangent lines that involves this Shanghai thing, having to do this. So it does come up. I don't think it's going to come up on this quiz Monday, but it is something we will see as we go along. Okay. So, seems like I'm missing something. What was the answer to that? Anybody get that far yet? 8 root 3 over 9, or is what they said if you're using the calculator. The area was 8 root 3 over 9. It happened at root 3 over 3. I think the x value was root 3 over 3. Oh, that's when you looked at it. You had root 3 over 3 and then thought,
I was stupid.
no, you looked it up in the back. Well, I probably told
3 is the answer.
I probably told you were stupid. I for different reasons than this problem. And that is no root 3 over 3 is like points.
But is it 8 root 3 over 9?
Oh, what's 8 root 3 over? Yeah, 1.5, 1.6, something, 1.539. That sounds about right. Yeah. Yeah. Because you got to answer the question, right? Because I remember you did say something about root 3 over 3, but then you looked up and back and said 8 root 3 over 9 or something. Because the question asked for what? Asked for the area, asked for the minimum area, right? The x is where, the x value is where that point is. So the root 3 over 3 is that point right here, was like 0.6 something, whatever root 3 over 3.
So then what would you
0.5
have to use that to then find those 2 points?
Well, you would then, no, you would take, you would just plug it into this. Yeah, you would just take root 3 over 3 and plug it into your area equation. Yeah. Now, list of candidates, I mean, let's finish this up. What are their endpoints? I mean, well, oh, wait, time out. Where's the derivative undefined? A prime is going to have an x on the bottom, I think. It'll be at 0.
That's
And that's also one of the candidates too, right? Yeah. So 0, x could be 0. And what's the most x could be? No. Remember, x is the coordinate of this point. When you drag it, it could be more than 1, right? Because you can't go down below then. So it could only go to here, so it's 1. Right? So your endpoints are 0 and 1. I think 0 was one of the candidates where the derivative is 0. Well, it's actually where it's undefined. So when you put it in, when you put a 0 in, you don't get any area. It's undefined. Well, that's because of that infinite. It'd be infinite area. So that's clearly not a minimum. And then you can put in 1, and then you can put root 3 over 3, which is where the derivative is 0, and it turns out. Oh, and it is plus or minus. Well, and all that does, I'm glad you said that, because that's just the other side of the triangle, right? Negative root 3 over 3 would be just the point that touches over here. So I usually just deal with this side, because as you move this point, that's going to move this point too. All right. So, yeah, because when you put that negative root 3 over 3, it's squared everywhere. Well, except there. Do you end up getting negative area? Well, you might with negative root 3 over 3, but I guess you just have to understand that that would be that point. All right. I think so. I think root 3 over 3 with the number line would actually be okay here. Because what happens is when you get up here, the area starts going down, 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 down until here, then the area starts going up, up, up till there. 1 truly is an endpoint there, but they told you in the problem you were limited from -1 to 1. So yeah, I think a 1 candidate thing with a number line would be okay there. All right. Yeah, the endpoints in the real life kind of problems, the endpoints don't come up very often as actual max and mins, but we don't want to forget about them. That's why I'm so picky about you writing all this down, that you discuss end behavior, you discuss where the derivative is undefined, because if you don't, then when you run into a problem where it does happen, you forget about it. And we have one we're going to do actually tomorrow. Well, I think there might be one in today's homework where the endpoint does become a pretty big factor. All right, let's go ahead and start a new problem here that is going to be on your homework, or that is part of your homework. So we'll just get your homework paper out and open up there to that same page, 241. And, oh yes, I knew I was reading this. But go ahead and get your book open, and we'll start this problem in a second. But I do have just a couple of quick things to talk about in this. Our book does not have very good or hardly any business type examples. And so I had to go to a different textbook to get some. And I just call this the business packet. Okay, so in your homework, I think it's got 4 problems out of our book for today, 4.3 day 2. It's got 4 problems out of our book, and then 2 out of this business packet. Now, I just photocopied the whole chapter, or the whole section out of this book. Turn to page 216 in this packet. 216. There's a little chart there. Okay, Now, several terms that we want to just be familiar with in the business problems. First of all, and it says it right on there, X is going to typically be the number of units. So when you're doing a business problem, like you're creating or selling some product, X is typically the number of units. That doesn't have to be, but often it is. So X is typically number of units. Lowercase p is typically the price per unit. Okay? The price per unit. Now, sometimes that's not a fixed price. Sometimes that's variable, depending on how many you produce. So sometimes P is actually a function. Little p is actually an equation that has X in it. Okay? Because maybe the more you make, the price may go down. And that's that first graph. They have those 4 graphs there. That first graph they call the demand function. Right? As demand increases, the price often goes up, or vice versa, right? It depends. Or if you make how many you make, right? If you make too many or you make more, sometimes the price goes down and that kind of thing. So that's there's a whole bunch of stuff you learn in business classes about demand and prices and stuff like that. But basically, P is the price per unit. Revenue, capital R, is typically, that's revenue, okay, that's the money you bring in. Typically, that's X times P, right? It's the, and we're going to assume the number, in all the problems we do, keep it simple. The number of units we produce is also the number of units we sell. So we're always going to sell everything we make. We'll just make that assumption most of the time, okay? So the number of units times what we get for each one, that's our revenue. That's how much money we bring in. All right, our cost, of course, is just the cost for producing these things. And that could be made up of multiple things. It could be your labor cost, it could be your materials cost for making the things, it could be your overhead like rent on your buildings, electricity, utilities, those kind of things. Okay, so those are wrapped up in the cost. And then the last thing, profit, which is what we're mostly interested in, is revenue minus cost. And that's a formula you want to make sure you understand, right? It's the money you bring in minus the cost to produce it. And that's your problem. So if you're doing a max profit problem, that's what you want to set up. You want to do your revenue minus your cost. Okay, so we need to be familiar with these terms. Then the last thing, P prime, R prime, C prime, they use the term marginal. So whenever you hear about marginal profit, they're talking about the derivative of zero. So a business person is interested in their marginal profit. They would be interested in their marginal profit equaling zero. Because what's that mean if P prime is zero? That's your max. That's when your profit is going to be at a max, when P prime is zero. So what if they do some calculations, they look at their quarterly sales or whatever, and they, and this is what managers do and so forth, and this is why management majors take classes in finance, and you have to take a business calculus and stuff like this. And they run the numbers, and they find out that their marginal profit, this is the language they would use, they wouldn't use derivative, they wouldn't say P prime, they would use this term. They find their marginal profit is positive. So what's that mean? They should have made more, right? If their marginal profit is positive, that means P prime is positive. That means they could sell more and increase their profit. They're making a profit, but they could do better. What if their marginal profit is negative? Yeah, they probably should make less, which means maybe they shut down a factory. Their costs are too high, maybe, right? So maybe they shut down a factory. Lay off some workers, right? You hear about that in the news sometimes, right? They'd be better off producing less. They would get more profit, okay? And so those are the things that they look at, okay, to make those kinds of decisions. It's not always, hey, open up new factories, make more things, we'll make more money. There's a lot of factors that go into that. All right, so those are some of the terms you'll hear in some of the problems, but the way of doing it is still the same. If you want to do max profit, you need to get a profit equation, do the derivative, set it equal to 0. You want to, oh, and there's one other one there, C bar. C bar is cost per unit. So it'd be the total cost divided by the number of units. So you might get a problem where they say find the minimum cost per unit. So they want the C bar equation and do the minimum of that. So you do the derivative, set it equal to 0, see if it's undefined, check endpoints, right? You go through all the same stuff. But it's just terms that you want to be familiar with. All right, now let's get into the homework. So let's look at the book problem, number 28. That's the one we're going to start with. We're going to start with number 28. And we're going to start with part B.
Is this on our homework?
This is actually on your homework. So you can go ahead and get your homework paper started out here. Okay? You have 4 book problems. This is one of them. It has 4 parts. You can skip the last part. You don't have to do part D. Part A is pretty easy, especially after you see parts B and C, which seems kind of strange why it would be part A. Okay? But I want to do part B. And part C is very similar to part B. So once we went through part B, that should help you in part A, or part C, excuse me, and part A. So if you read the problem, number 28, it says Federalist Express limits the size of a mailable parcel, the longest side plus the girth, which is the perimeter of a cross-section perpendicular to the long side. The long side plus the girth may not exceed 108 inches. Part B says find the dimensions of a mailable rectangular parcel with a square base that has the largest volume. Hint, consider 2 cases depending on which side is longest. Okay, so we'll deal with that 2 cases thing here in a second. So we're going to do a rectangle. So I'm going to start with a picture. It's got a square base. So I got a rectangular box. Right? That I want to mail. I want to find the largest box that I can make with that limitation that they have with the 108 inches, which we'll get to in a second. So step 1 is what? Volume is what we're looking for. So V equals. Step 2, write an equation for volume. What is it? Length times width times height. 3 variables, that's not good. Oh, but they said it had a square base. And I'm not crazy about using L, so maybe I'll use X. I'm going to use X, X, and Y. I mean, I don't care, use L and H, whatever. But if I use X, X, and Y, it might be nice. So now what's my volume? X squared Y. Okay, that's better. 2 variables. Step 3. Step 3. Get this in terms of 1 variable. Well, that's where the 108 is going to come in. So what did they say? So the longest side, oh, so this is why they talked about 2 cases. Because I happen to draw mine with the longest side being the height. What if it was a short, fat box? Then the longest side would be X. So we have to consider both of those situations. Okay? So we'll get to the second situation here in a minute. So 28 has several parts, and each part has several parts. So that's why there's not that many problems. All right. So the long side is Y plus the girth. No, it says the long side plus the girth can't go over 100. So the girth would be 4x. Girth. I mean, I think of it this way. I think you know, my girth is getting larger and larger all the time. And when I think of my girth, it would be around here, right? Here's my long side, up and down, but although this is getting closer to being the long side all the time. But anyway, so yes, the girth, what it says is the cross section, the perimeter of the cross section perpendicular long side. So long side's here, perpendicular would be here, and it's a perimeter around it. So perimeter, okay, it would be that right there. So that'd be x, 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 x. It'd be the distance around would be 4x. So y plus 4x cannot exceed 108. So you might say, well, you could put less than or equal to 108. Well, it doesn't make sense that the largest box you could do would be the one that uses all 108 inches. So I would say just do equals 108 instead of less than or equal to. Okay? Which is, I think that's a fair assumption to make, that we want to use the full 108 to get the largest volume we could. All right, now where do you go from there? Solve for y. So now it looks a lot like the problems we've already been doing, right? And there isn't anything new in the problems today. It's just more of the same, following the kind of the recipe and that kind of thing. And so I'm going to stop right there on this one. So now it's a lot like number 9, number 11. We want to find the max volume, do the derivative, set equals 0. Where's it undefined? What about endpoints on this? So this could be another one of those where you could not do endpoints and do it as a number line. Because 0, let's face it, there's no box if x is 0. So that's clearly not going to be the largest volume. But if we are going to go the endpoint route, what's the biggest x could be? 108 divided by 4, 27. Because that means you'd have no y. So the biggest x could be would be 27. That would use up all 108 for the x. But again, there's not even going to be boxes at those sizes. So if you want to do this as a no endpoint problem and do it as a kind of a number line kind of situation, you could do that. All right, now, before I let you go on your own, we got to consider the other situation. If we have a short fat box like this. All right, so you have this situation here. So now it's x, x, and y. Now your volume is still x squared y, but now your girth is different. And remember, it's the long side plus the girth. So it would be x plus, yeah, I think your girth this time, if this is our long side, actually there's two of them, but I'll just use this one. Perpendicular to that would be here, right? Wouldn't it be that girth? So that would be y, x, y, x. So it'd be 2x plus 2y. So it'd be x plus 2x plus 2y would have to equal 108. So that's why it's a different. So you should get a different volume. And then the answer to the question is going to be whichever those two is biggest. So we'll do a max on this situation, and we'll find out the biggest box we could have where the height is the tallest. And then we'd find the biggest box we could have where the width is the tallest, or the biggest side. And then of those two, which one would give us the biggest volume? Okay? All right. So I'll let you finish that. Then C is the same thing except with spheres. Or excuse me, not spheres, but cylinders. So you could have a taller cylinder, or you could have a short, fatter cylinder, where the long side is across as opposed to tall. Now what's the volume of a cylinder? Pi r squared times h. Pi r squared. I mean, come on, it's 7th grade, isn't it?
That's a long time ago.
Well, that's true. All right. Pi r squared h. Pi r squared h. All right, so that's 28C. All right. Go to work. You may.